Hi, I'm Norman Wildberger. Today we're going to make the transition from studying triangles, namely 3 points in the plane, to studying 4 points, leading us to the theory of quadrilaterals. Now in this theory there is one formula or relation that stands out as being particularly important, and that was derived by Euler. Or actually it's a consequence of a formula that Euler derived for the volume of a tetrahedron in 3-dimensional space. But when we restrict it to 4 points lying in a plane, then we get a relation between quadrances determined by 4 points. And that's what we're heading for. We're heading to try to understand what that relation is and try to find it. And today I want to introduce a preliminary aspect of that. We've got 4 particular points, A, B, C, D. This one's 5, 2, this one's 3, 4, this one's minus 1, 3, and this one's the origin 0, 0. And these 4 points determine 6 quadrances, which are shown here. And we'll suppose that we know 5 of these 6, and we want to find the 6th one. So suppose that the quadrants from A to C, which we happen to know is 37, suppose we didn't know what that was, but we knew what the other 5 were. How could we find the 37? Alright, so our strategy is going to be roughly this. We're going to look at this configuration here, and we're going to first find the spreads. This one here, S1, this one here, S2, this one R1, and this one R2. That will be relatively easy because we know these 3 quadrances and we know these 3 quadrances. Then we'll use the triple spread formula and the cross law to get at Q. So here is our quadrilateral again, A, B, C, D. And now we suppose that we don't know the actual positions of the points, but we just know the quadrances 29, 8, 17, 10, and this diagonal one, 25. And we're trying to figure out what this quadrant's Q is. Alright, so our first thing to do is to find the spreads. And you know how to do that because you can use the cross law in this triangle and in this triangle to find all of the spreads of those triangles. And this spread is 196 over 725. This one's 169 over 250. This one's 49 over 50. And this one's 169 over 425. So I'll leave that calculation for you as an exercise. And now let's suppose that the spread between these 2 lines right here is S, and the spread between these 2 lines is R. Now the spread S and this spread 49/50 and this spread 169 over 425, they form a spread triple. In other words, those 3 spreads satisfy the triple spread formula. And that gives a quadratic equation for S. So by now I hope you can write down the triple spread formula by yourself. And here's the quadratic equation that we get in a particularly simple form where the S just appears there. So we've already completed the square there. And I just point out that this number here is obtained from these 2 spreads. It's this spread plus this spread minus twice the product. And what's appearing on the right hand side here is 4 times this times 1 minus this times 1 minus that. So that quadratic equation has 2 solutions, and there they are right there. In an exactly similar way, the triple spread formula applied to these 3 spreads here gives a quadratic equation for R found from these 2 spreads. And that quadratic equation has 2 solutions, and there they are right there. So at this point we have 2 possible spreads for S, 2 possible spreads for R. And it seems as if there may be then 2 times 2 or 4 possible combinations of answers that we need to consider. But intuitively we should feel that there's only really 2 solutions, because if we know these 5 quadrances, then this situation is already determined up to one particular ambiguity. If we take this triangle DBC and we fold it over on this line here, then all those quadrances stay the same, except for Q, which will change. So we kind of expect that there's going to be two possible values for Q. So how do we get two possible values from the 4 that this suggests? We need an extra piece of information. And that extra piece of information is obtained from the cross law by looking at these two triangles, this one right here and this one right here. So in this triangle here, we have a spread of S, we have quadrant 17, quadrant 8, and the unknown quadrants Q. There's the cross law in that triangle. Q minus 17 minus 8 all squared is 4 times 17 times 8 times 1 minus S. And in this triangle also we get a cross law, which has a similar form. Now while both of these equations involve the unknown quantity Q, it turns out that we can use them to get a relation between S and R. And that involves a nice trick that's very important that you know. We'll call this the quadratic trick. And it is that two quadratic equations give one linear equation. So if we take those two equations that I wrote down on the previous page, I called them 3 and 4 there, and we just write them out and put everything on one side. And what we can do with them is we can take the difference to get rid of the quadratic term. If the two equations had different coefficients here, then we would have to take a linear combination of them to get rid of the Q squared. But when we do it in this case, it's particularly simple. We just take equation 3 prime minus equation 4 prime, and we get this linear equation in Q. We can solve for Q, just bringing everything to the other side, dividing by 28, and we get 10 minus 136 over 7 times S plus 290 over 7 times R. So what do we do with that? That's a very nice equation. We can substitute that back in to either this equation or this equation, giving us then an equation that only involves a relation between S and R. And it's a little bit complicated, but not too bad. It has exactly this form. It's a quadratic equation with an S squared in it, an SR, so R squared, and linear terms S, R, and a constant term. And the coefficients are a little bit big, but that doesn't bother us. This gives now an extra condition on S and R. The two values that we choose have to satisfy this additional condition, and that allows us to reduce from 4 possibilities that we had initially to simply 2. And now we can check that of the 4 solutions that we had originally for S and R, these two satisfy that new condition. And if S and R have these values, then the formula for Q on the previous page gives us Q equals 37. And the other possibility is that S and R have these two values. They also satisfy the condition, the quadratic condition that we've determined. And in that case, Q becomes 197 over 25. So we've solved our problem. We have found the two possible values for Q. And both of these values are legitimate. One corresponding to the picture that we started with, another corresponding to a different picture where the triangles overlapped in a different way. So there are 2 solutions suggesting that the ultimate relation between these 6 quadrances, in general, not just in a particular case, is going to be a relation that's quadratic in any one variable. Next time I'm going to share some perhaps unorthodox thoughts about what geometry is really about. I hope you'll join me for that. I'm Wildberger. Thanks for listening.